All right, I've put together a few more examples of using the principle of superposition with electric forces and electric fields. So just to start off, we are going to review the difference between the electric field versus the electric force. Okay, so in this situation, if we have point A, all right, and then we have Q1, which is positive, and we have Q2, which is negative. If we were looking at the electric fields, we know that Q1 is electric field is moving in that direction, and then Q2, because it is negative, it is moving in this direction. So these two electric fields would actually be opposites of each other, and so they would subtract. Okay. Now Q1 has a larger charge, but it is at quite a bigger distance than Q2. So really, it doesn't matter which one you make positive or negative. You can make Q2 negative since it has a negative charge in there, or you can calculate using the absolute values and then determine based on a diagram like this. In Expert TA, they often tell you what direction should be positive or negative, and so you should follow that. All right, and so in this situation, we would have the electric field at point A would actually be the electric field from 1 plus the electric field from 2. And again, in this case, I would make sure that my electric field for 2 is negative with that negative charge. So we've got for the field 1, we've got KQ, which is your 8 microcoulombs, divided by the radius, and note that radius would be that full 6 meters. Our electric field 2 would be the KQ, which would be 2 microcoulombs or negative microcoulombs with our radius of 2, which would be the r squared. And so you can solve in that manner. Okay, the difference between the electric fields versus the electric force is that your electric force would actually have to have a charge here at A, because if we're looking at our Coulomb's law, we're looking at the charge of this point A. So QA would have to have some sort of a charge. Let's call it, 4 microcoulombs. All right, and so in this case, if we keep that positive, we can actually determine, so our total force in this case would be the sum of the two forces. So that would be the sum of force of Q1 on QA, and then we would add also the force of Q2 on QA. All right, so at this situation, our Q1 is positive and our QA is positive. So our force for A, for 1 on A, would be in that direction. However, our negative is going to attract it. So our force from Q2 on A is going to be in the opposite direction. So once again, you can include the sign in your calculation that would make your overall force negative. Or if you were looking at the absolute values and then look at your vector diagram to determine whether you are adding these vectors or subtracting. All right, so the main difference here really is when we're dealing with our fields, we are just dealing with the charges, the source charges, at a specific distance. When we're dealing with our forces, the point at which we are determining is also going to have a force, and we're going to look at those individual forces and add them up. So in this situation here, we're asking for determining our electric field at point P. All right, and so this one is not linear. And so we're going to walk through a little practice problem. I also will post pictures of my solutions since I am not very good at writing on this tablet. Okay, so for this one here, we've got two things going on. They're both positive charges. All right, and so we've got, I'm going to go ahead and call this our Q in the X direction. So our electric field is moving in the X direction there. And then this one is going to be our Y direction. And in this case, it is moving in this direction here. All right, and so we've got these two vectors and we can solve for them separately. Okay, so our electric field, and again, we're doing electric field. Our electric field in the y direction is going to be K, I'm going to call that QY over R squared. All right, which in this case would be our 8.99 times 10 to the 9 multiplied by 2 times 10 to the negative 6 divided by our R, which is our 4.0 meters. So our field in the y direction here is going to be 1,124, and that is newtons per coulomb, and that is up in that direction. Okay, so then if we look in our x direction, I'll do this down here. Again, we're using KQ in our x direction over our R squared. So in our x direction, we still have our 8.99 times 10 to the 9. And then we've got 2 times 10 to the negative 6 over, and this time we've got 7 meters squared. Ran out of room there. And in this case, we end up with 367 newtons per coulomb. All right, so we know here from our diagram, we've got 376 newtons per coulomb in that direction, and then we've got 1,124 in that direction. All right, so if we take a look at this, and let's redraw this here, because we're doing our vector addition. All right, so we know that this is going to result in something going in that direction. Our y is a little bit stronger, so it's going to be a little closer to vertical, but we know it's going off in that direction. Okay, so in this case, we can take a look at, if we draw this out, we can have, this is our y direction, and then this is our x direction, right? Because anytime we do vector addition, we add them tip to tail, head to tail, whatever the term you like to use, and then this would be our resulting vector. So this is our grand total force, taking into consideration both, sorry, they are not forces, they are fields. My apologies. So our fields in these directions are going to add up, and we have to use that vector addition. Luckily, we know good old Pythagorean theorem in order to figure this out. So our total field is going to be E in the x direction squared plus E in the y direction squared is going to be E total squared, right? And so we are going to determine it like this. So we're plugging in our x and y directions here, and that should leave us with a total electric field of 1,182 newtons per coulomb. Okay. Now, it says electric field. It doesn't ask specifically for magnitude or direction, so we're assuming it's wanting both of them. If a question just says, what is the magnitude of the electric field, then we would be done here. Okay. Now, we know the relative direction is in here at some point, but we need to go ahead and actually solve for that. So to do that, we need that lovely little angle. Whenever I do problems like these, I try not to use ones that I've calculated. Obviously, we've calculated 3 different answers here. So we have all 3 sides, so you really could pick your favorite trig function. I'm going to go ahead and use tangent of theta, which is going to be my E y over E x. And I personally use these because we've had to calculate EY and we've had to calculate EX, and then we're using both of those calculations to calculate E total. So I like to use ones that have been less calculated or ones that have been given to us, but either way, any 3 of those, you pick 2 of the 3, just use the correct trig function. Please note you cannot use the distances. The distances in these situations are not giving you the correct angle because we are actually looking at the fourth strength, and that has to do with both of the distance as well as the charge. So we have to use the vector of the electric field. So when you divide these two and then inverse tangent, I have an angle of 72 degrees. If you're getting a funky answer here, double check that you are in degrees and not radians, but that should give you about 72 degrees. All right, so our grand total answer would be this electric field is 1,182 newtons per coulomb, 72 degrees above the x-axis. All right, so that is two-dimensional electric fields. Let's go ahead and look at two-dimensional electric forces. So for this particular electric force, it is asking what our force is on Q1. This is going to make our lives a little bit easier because we have two different things going on, but they're not actually, we don't have to worry about breaking components just yet. So the force on Q1, so Q1 is down here in the corner, okay? And they are both positive, all right? And so they are going to, Q3 is actually going to be applying a force in this direction on Q1, okay? Then we also have in our X direction, Q2 is applying a force in this direction here, also on Q1. Okay, so we have two independent X and Y directions, and then we can find the resultant once we have the individuals. All right, so if we start with our Y direction, you could start with any direction really. Okay, but I'm going to start with our Y direction. So I'm going to call this our force of 3 on 1. And we are using our force in this case. So we need our Coulomb's law equation. All right, and so just for the lack of not having a lot of room, I will jump to the end here. So we have 8.99 times 10 to the 9 multiplied by 3 times 10 to the 9 10 to the negative 9 because it's a nanocoulomb, multiplied by 3 times 10 to the negative 9 for Q1, divided by 0.04 squared for our radius, and this gives us a total of 3.37 times 10 to the negative 5 newtons. Okay, now if we look in our X direction, we've got the force of 2 on 1, which again, we're gonna have KQ2, Q1 over R squared. So when you're plugging everything in, please make sure you're paying attention to your exponents. We have a lot of scientific notation here, and just double check you're doing them positive or negative when necessary. So K is our 8.99 times 10 to the 9. That's going to multiply by our Q2, which is 1 times 10 to the negative 9, multiplied by Q1, which is 2 times 10 to the negative 9, divided by this distance, which is 0.07 squared. Pull all of that into your calculator properly, and I ended up with 3.67 times 10 to the negative 6 newtons. All right, so if I were to redraw this, again, we know that our resultant is going to be in this direction some way, but we have to properly draw our triangle using proper vector addition. Okay, so I'll go over here. This is our force of 3 on 1, and then if we add them tip to tail, we have our force of 2 on 1. These are not even close to drawing to scale because we can see how much smaller this horizontal force is going to be. Okay, and so we end up with our resultant force in this direction. So once again, we can use our good old Pythagorean theorem, and our force is going to be the square root of force of 2 on 1 squared plus the force of 3 on 1 squared. Again, really pay attention to where you're using parentheses. I will actually write this out and show you how I do this in my calculator. Okay, I square root at the end, so I'll figure out this answer first and then do square root answer. Okay, but when I actually plug this in, I put parentheses everywhere. Okay, so we're going to do 3.67 times 10 to the negative 6, parentheses squared. And then I would add that to, I actually double parentheses these just to be on the safe side. You don't have to, but I like to. I'm a big parentheses fan of my graphing calculator. So I always throw parentheses before the square just because you want to make sure that it's squaring the whole number and not just the exponent, okay? So I would type both of these in, add them up, and then do, your second function square root, second function answer to get your grand total force, which is going to be 1.87 times 10 to the negative 5 newtons. Again, it depends on where you're around. I'm keeping 3 significant figures in all of this. If you kept a little bit more, you may have something slightly different, but again, within that 10% range is always acceptable in my mind, okay? And that's why I have you guys show your work so I can see where you rounded. Definitely keep a few significant figures here, even though the question is only giving us 1 significant figure in each of the variables. Try to keep 2 or 3. Otherwise, that's just a lot of rounding. Okay. And again, if it is asking for a direction, this would be our angle right here from the beginning of our force. Again, I'm going to go ahead and use tangent of theta, which would be my F2 over 1 divided by my F3 on 1. Okay, so use your favorite SOHCAHTOA. You get the inverse. I'm doing the inverse tangent here. So in this case, I get a very small angle of 6.2 degrees. So again, my triangle is definitely not to scale. But we know that that looks about right because my y direction is so much bigger than my x direction. Okay. So in this case, we have 1 vertical force, 1 horizontal force. We find the hypotenuse and we find the angle. Again, the angle is only if it is asking you for the full vector. If it asks for just the magnitude, this is your magnitude here. Okay? Now, here comes the extra fun part. What if we ask what the charge or what the force is over here on Q2? Okay. So in this case, we still have a force in the x direction. Our force of Q1 on Q2 is going to be in the x direction. However, in this case, we have our force from Q3 on Q2 is actually going to be on that angle. Okay. So if I were to redraw this, if this is my force here, this is my force of 3 on 2. Okay, and then this is my force of 1 on 2. So what we're going to end up having to do is break this diagonal force up into its own vector components. So we cannot do that using distances or charges. We have to use those vectors. And then notice that this x direction is actually the same as my force of Q1 on Q2 direction. So we'll have to end up adding those before we find our resultant. Okay. So to start off, I'm going to go ahead and deal with our force of 3 on 2. All right. So I'm dealing with this one here, our force of 3 on 2 first. Okay. You can do the other one first if you want, but this is what I'm going to do. So my force of 3 on 2, I'm going to use Coulomb's law. Okay, now in this particular situation, I don't actually have my radius. However, luckily I have my good old Pythagorean theorem. So I can do 0.04 squared plus 0.07 squared and then take the square root of that. So that distance here I calculated to be 0.0806. I left that to 3 significant figures. All right, now keep in mind that we can use these distances here because these are in place. A field, remember your field kind of, your point charge stays in one place and then the field radiates outwards, but we're looking at a specific distance here. So these charges are stationary, so we can use those distances to find both the distance of that hypotenuse, and we're actually going to use that to find this angle here once we have to break that into x and y components. Okay, so going back to force 3 on 2, we've got our 8.99 times 10 to the 9, and then we've got 3 times 10 to the negative 9, and our 1 times 10 to the negative 9. All that, we're using this distance, so our 0.0806 squared will give us a grand total force of 4.15 times 10 to the negative 6 newtons. Okay, so that is this full force here. All right, so that force we are now going to have to break into a y component and its own x component here, so we can add our two x components. Okay, so I'm going to start with the y. Actually, it really doesn't matter which we start with, but we can start with the y. So in this situation, we're going to have to determine what this angle is. Okay, and again, I like to use given values. So in this case, I did the tangent of 0.07 divided by 0.04 to find the angle. You take the inverse tangent, and I ended up with an angle of 60 degrees. I think it was like 60.1 or something, but I decided to use 60 degrees as that angle. Okay, so in order to find our y direction, so I'm going to call this f of 3 on 2 in the y direction. Okay, so that is this component here. I'm going to use my cosine, right? So the cosine of 60 is going to be this unknown, over the hypotenuse, right? The adjacent over the hypotenuse. So if I'm solving for the y component, it's going to be f of 3 on 2 times the cosine of theta. All right, so I'm going to plug in my 4.15 times 10 to the negative 6 for my force of 3 on 2 and multiply that by the cosine of 60. So my y direction for this force is going to be 2.075 times 10 to the negative 6 newtons. And then I'm going to do the same to find this horizontal component. Sorry, this horizontal component here. So in this case, I'm going to use the sine. So my 3 on 2 in the x direction is going to be the total 3 on 2 force times the sine of 60 degrees. And for this, I got 3.59 times 10 to the negative 6 newtons. Okay, so what I did there is I took this force and I broke it up into an x and y component, so I can now figure out my two x's and add those together. Okay, so we need to figure out our original f of 1 on 2. So f of 1 on 2 is going to be our k q1 q2 over r squared. All right, and that is our, I'm just going to write k. We know it's 8.99 times 10 to the 9. Our q1 is 2 times 10 to the negative 9 multiplied by 1 times 10 to the negative 9 divided by our 0.07 squared, and this gives us, we actually did this in the last problem too. Which gives us, I've just lost my place. There it is. Okay, I found it. 3.67 times 10 to the negative 6. Sorry about that. Got a lot of numbers here. Okay, so we know that we have the original Q1 on 2 in the x direction, and then we have to add the x component of force 3 on 2. So we're going to add those together to get a grand total F in the x direction. So when I add those two numbers together, because they are in the same direction, I get 7.26 times 10 to the negative 6 newtons. Okay, so just to recap, okay, we have a force in the x direction from Q1 on Q2, and then we have a force on a diagonal for Q3 on Q2 that we broke up into x and y components. We then added all of the forces in the x direction. So we added these two numbers to get the total in the x direction. We only have one force in the y direction. So now we can take these two forces. So we know our F of x is going in this direction. We know our F of y is going in that direction, which would mean our grand total force is in this direction. And we can go back to using our Pythagorean theorem. So our total is going to be the square root of F in the x direction squared plus F in the y direction squared. Okay, and again, I'm using this number here in my x direction because that is both x's combined together. Please be careful of your parentheses when typing this all into your calculator. And if you do it correctly, and assuming I did it all correctly, we get 7.55 times 10 to the negative 6 newtons for our total force on Q2. Okay, so Q2 has a resulting force in that direction. If we need to find the angle for that, then we would use the the tangent, and we can determine the sign. In this case, we're just going to look at the magnitude because we've done a lot for this one. Okay, so once again, in this situation, you really have to break things down into x and y components, keep everything straight. I obviously like to color code mine, and you can figure out a system that works for you to label them or to keep things organized. Okay, so hopefully this helps with our two-dimensional force and our two-dimensional field equations. And as always, reach out if you need more help.